A quick show of hands, how many of you ever wanted a database that provides predictable performance, higher availability, and is fully managed? Awesome. I was expecting 100% of you will say yes. So we are in the right room. And today, what I'm going to do in this talk is talk about evolution of a hyperscale cloud database service, which is DynamoDB. Talk through the lessons that we have learned over the years while building this hyperscale database. And I am Akshat Vig. I'm a principal engineer in Amazon DynamoDB team, and I've been with DynamoDB right from its inception. So with that, let's jump in. AWS offers 15 plus purpose-built database engines to support diverse data models, including relational, in-memory, document, graph, time series. So the idea is that you as a customer can choose the right tool for the use case that you are trying to solve. And in this talk, we are zooming in into DynamoDB, which is a key value database. So first question that comes to mind is why DynamoDB? And let's go back to history. During 2004-2005 timeframe, Amazon.com was facing scaling challenges caused by the relational database that the website was using. And at Amazon, whenever we have these service disruptions, one thing we do as a habit, as a culture, is we do COEs, which are basically correction of errors. And in that COE, we ask questions. How can we make sure that the issue that happened does not happen again? And the use case that for which we were with that particular outage happened was related to a shopping cart. So one of the questions that we asked in the COE was, why are we using a SQL database for this specific use case? What are the SQL capabilities that are actually needed? And turns out, not many. And choosing the right database technology is the key to build a system for scale and predictable performance. And at that time, when we asked this question, if not an SQL database, what exactly would we do? At that time, no other database technology existed that met the requirements that we had for the shopping cart use case. So Amazon created Dynamo, and it was between 2004 to 2007 where Dynamo was created. And finally, in 2007, we published the Dynamo paper after letting it run in production and used by not just the shopping cart use case, but multiple Amazon.com services. So Dynamo was created in response to the need for a highly available, scalable, and durable key value database for the shopping cart, and then more and more teams started using it. So Dynamo was a software system that teams had to run the installations on resources that were owned by them, and it became really, really popular inside Amazon within multiple teams. And hearing this, one thing we heard from all these teams is that, hey, Dynamo is amazing, but what if you make that as a service so that a lot of teams who are trying to become experts in running these Dynamo installations, it becomes easier. That led to the launch of DynamoDB. And Dynamo and DynamoDB, they are different. So Amazon DynamoDB is a result of everything we have learned about building scalable, large-scale databases at Amazon, and it has evolved based on the experiences that we have learned while building these services. And there are differences between Dynamo and DynamoDB. For example, Dynamo, as I was saying, it was single tenant. As a team, you would run an installation, you would own the resources that are used to run that service. DynamoDB is multi-tenant. It's basically serverless. Dynamo provides tunable consistency. DynamoDB is opinionated about it and provides strong and eventual consistency. Dynamo, it prefers availability over consistency, versus DynamoDB prefers consistency over availability. In Dynamo, routing and storage are coupled, and we'll see in this talk, routing and storage in DynamoDB are decoupled. Last, custom conflict resolution was something that was supported in Dynamo. In DynamoDB, we have last writer wins. So there are differences between Dynamo and DynamoDB. So coming back to the question of like why DynamoDB, and if you ask this question today, 10 years later, customer still will say they want consistent performance, they want better performance, they want a fully managed serverless experience, they want higher availability for on their service, and we are seeing that like consistent performance at scale. Dynamo, this is one of the key durable tenets of Dynamo, key properties that Dynamo provides, that as Dynamo is being adopted by hundreds of thousands of customers, and as the requests are increasing, even though request rates are increasing, customers who are running mission critical workloads on DynamoDB, the performance they are seeing is consistent. They're getting consistent performance at scale, and proof is in the pudding. Like one of the customers, Zoom, in early 2020, when they saw like unprecedented usage that grew from 10 million to 300 million daily meeting participants, DynamoDB was able to scale with just a click of a button and still provide predictable performance to them. Quite amazing, right? Now, DynamoDB is fully managed. What does it mean? Like DynamoDB, I would say, was serverless even before the term serverless was coined. You pay for whatever you use in DynamoDB. You can scale down to 0 essentially. If you're not sending any requests, you don't get charged for whatever you're doing. It is built with separation of storage and compute. As a customer, in case you run into like logical corruptions where you accidentally deleted some of the items or deleted your table, you can do a restore. And Dynamo also provides global active replication, where you have use cases where you want the data closer to the user, so you can run DynamoDB table as a global table. On availability, Dynamo offers an SLA of 4 nines of availability for a single region setup, and if you have a global table, then you get 5 nines of availability. And just talking about like magnitude of scale, to understand that, like Amazon.com being one of the customers of DynamoDB, 2022 Prime Day, they generated, like Amazon.com and all the different websites, 105.2 million requests per second. And this is just one customer. This can help you understand the magnitude at which DynamoDB runs. And throughout all this, they saw, predictable single-digit millisecond performance. And it's not just Amazon.com. Hundreds of thousands of customers have chosen DynamoDB to run their mission-critical workloads. So, introduction of DynamoDB. How is it different from Dynamo? What properties are kind of the durable tenets of the service? Now let's look at how it has evolved over the years, right? So DynamoDB over the years, it was launched in 2012, working backward from customer. That's how Amazon operates. It started as a key value store, right? We first launched 2012 DynamoDB, where you as a customer can do put, gets, and it scales. Foundationally very strong. Then we started hearing from customers, hey, we want more, query capabilities, search capabilities in DynamoDB, and we added indexing. Then customers started asking about JSON documents. We added that so that they can now preserve complex and possibly nested structures inside DynamoDB items. And then 2015, a lot of customers were asking us, hey, can you provide us materialized views? Can you provide us backup restore? Can you provide us global replication? So we said, okay, let's take a step back, figure out what common building block we need to build all these different things that customers are asking. And we launched DynamoDB Stream so that by the time we build all these native features inside Dynamo, customers can innovate on their own. And a lot of customers actually used like the basic scan operation and streams to innovate on their own. And most recently, we launched like easier ingestion of data into Dynamo or easier export of data from Dynamo. So over the years, the ask from customers around features, predictable performance, availability, durability, that has been like constant. So you must be wondering, how does DynamoDB scale and provide predictable performance? Let's try to understand this particular aspect of Dynamo by understanding how exactly a put item request works. So as a client, you send a request. You might be either in Amazon EC2 network or somewhere on the internet. It doesn't matter. Your request, as soon as you make a request to do a put item, it lands on the request router. Now, request router is the first service that you hit, and as every AWS call, this call is authenticated and authorized using IAM. Once the request is authenticated and authorized, then we look at the metadata. We try to figure out where exactly do we need to route the request, right? Because the address of like where exactly the data this particular item has to finally land, it is stored in a metadata service, which is what the request router concerns. Once it knows the answer where to route the request, next thing it does is it basically verifies whether the table that the customer is trying to use, whether it has enough capacity. If it has enough capacity, the request is admitted. In case the capacity is not there, request is rejected. So this is basically admission control done at the request router layer. Once all that goes through, request is sent to the storage node. And for every item in Dynamo, we maintain multiple copies of that data. And DynamoDB storage nodes, one of the storage node is a leader storage node, and the other two storage nodes are follower storage nodes. So whenever you make a write request, it goes to the leader, gets written on at least one more follower before the write is actually acknowledged back to the client. And we don't have not just a single request router and not just 3 storage nodes. The service consists of many thousand of these components. So whenever a client makes a request, the request is routed to a specific storage node and sent to the request router and then sent to the storage node. And AWS, just like a well-architected service, DynamoDB is also designed to be fault tolerant across multiple availability zones. And in each region, there are basically request router and storage nodes, which are in 3 different availability zones. And we maintain 3 different copies of data for every item that you store in the DynamoDB table. Now, request router essentially does a metadata lookup to find out where exactly to route the request, and it takes away the burden from the clients to do the routing. That's what it means by when I said storage and routing is decoupled. That's what I meant, that the clients now don't have to know about where to route the request. It is all abstracted away in the request router. So whenever the request router gets a request, it finds out the storage node that are hosting the data. It will connect to the leader storage node. The leader storage node submits the request, acknowledges, and finally, once it gets an acknowledgement from one more replica, it acknowledges it back to the client. Data is replicated at least 2 availability zones before it is acknowledged. Now, DynamoDB uses multi-paxos to elect a leader, and leader continuously heartbeats with its peers. And the reason it is doing it is that so that if a peer fails to hear heartbeats from a leader, a new leader can be elected so that availability is not impacted. So the goal is to reduce the failure detection and elect a new leader as soon as possible in case of failures. Awesome. So now we understand the scale at which Dynamo operates. We understand how the request routing logic works. Let's look at the logical construct, the table, and how exactly DynamoDB automatically scales as your traffic increases, as your data size increases in the DynamoDB table. So as a customer, DynamoDB, you create a table, and each table you specify a partition key. Now, in this particular example, each customer has a unique customer identifier, and we are storing customer information in this table. So customer ID is your partition key, and then you also store other customer information like name, city, etc. In the item as other attributes. Now, DynamoDB scales by doing partitioning, and how exactly that happens is, behind the scenes, whenever you make a call to DynamoDB with the customer ID or whatever is your partition key, Dynamo runs a one-way hash. And what the reason for doing that one-way hash is that we can it results in random distribution across the total hash space associated with that table. Now, one-way hash, it cannot be reversed. It's not possible to essentially determine the input from the hashed output. The hashing algorithm, it results in essentially highly randomized hash values, even for inputs that are very similar. Now, a table is partitioned into smaller segments based on the overall capacity that you have asked or the size of the table. And each partition, it contains a contiguous range of key value pairs. For example, in this case, we have a green partition that has values roughly from 0 to 6. Similarly, we have the orange partition, which has values from 9 to B. And then you have the pink partition, which has values from E to F, right? So essentially, given a hashed value of an item partition key, a request router can determine which hash segment that particular item falls into. And from the partition metadata service, it can find out the 3 storage nodes which are holding the copy of that particular item, and then send the request to that particular set of nodes. Now, as I explained previously, we have 3 copies of data in 3 different availability zones. So if we have these 3 partitions, essentially we have 3 green partitions in 3 different zones, 3 orange partitions, and then 3 pink partitions. And all these partitions, the metadata about where exactly these partitions are is stored in a metadata service. And that particular metadata is called as partition map. And what a partition map looks like, it essentially is the key ranges that partition supports, and then green 1, green 2, green 3, these are essentially the addresses of the 3 storage nodes where that data is actually, where that partition is actually hosted. Now think about it. When Zoom comes and asks for 10 million read capacity unit table, we would essentially add more partitions. If suddenly they increase their throughput to 100 million, corresponding to that, we would add more partitions, update the metadata, and that's how DynamoDB scales. Now, what challenges are there? I said DynamoDB is a multi-tenant system. So what are the different challenges that come into picture that we have to solve? What are the lessons that we have learned to provide predictable performance? And one of the common challenges in a multi-tenant system is workload isolation, because it's not just one customer that we have multiple customers. And these customers, their partitions are installed on these storage nodes which are multi-tenant, right? If not done right, if isolation is not done right, it can cause performance impact to these customers. So let's jump into how exactly we solve that. So in the original version of DynamoDB that was released in 2012, customers explicitly specified the throughput that the table required in terms of read capacity units and write capacity units. And that is, combined, that is what is called as provisioned throughput of the table. Now, if a customer is essentially reading an item which is up to 4 KB, that means it has consumed 1 read capacity units. Similarly, if a customer is doing a write of a 1 KB item, that would mean the write capacity unit is consumed. Now recall from the previous example for the customers table, we had 3 partitions, right? And if a customer asks for 300 read capacity units in the original version of Dynamo, what we would do is we would assign 100 RCUs to each of the partitions. So you have basically 300 RCUs in total for your table. And if your workload is uniform, assuming that your workload is uniform, essentially your traffic is going to 3 different partitions at a uniform rate. To provide workload isolation, DynamoDB uses token bucket algorithm. And token bucket is to track the consumption of tokens of the capacity that particular table has and a partition has, and enforce basically a ceiling for that. Now, looking at one of these partitions, we had token buckets at a partition level in the original version of Dynamo. And each second, essentially, we are refilling tokens at the rate of the capacity assigned to the partition, which is the bucket in this particular case. So when RCUs are used for read requests, we are continuously deducting them based on the consumption. So if you do one request and we basically consume one token from this bucket, the bucket is getting refilled at a constant rate. If the bucket is empty, obviously we cannot accept the request and we ask customers to try again. So overall, let's say that the customer is doing like sending request, and if there are 100 tokens, the request will get accepted for the green partition. As soon as the consumed rate goes above 100 RCUs, in this particular example, as soon as it reaches 101 RCU, your request will get rejected because there are no tokens that are left in that token bucket. So this is, a high-level idea of how token buckets would work. Now, what we found out when we launched DynamoDB is that uniform distribution for the workloads is very hard, and essentially getting uniform workloads across for the full duration of when your application is running, your table exists, it's very hard for customers to achieve that. And that because the traffic tend to come in waves or spikes. For example, let's take an example. Let's say you have an application which is for serving coffee, right? You suddenly will see that spike happening early in the morning, right? And then suddenly your traffic will increase as most of the customers get the coffee, they go to their office. What you'll see is the traffic suddenly drops. So traffic is not uniform. It basically changes with time, right? Sometimes it is spiky, sometimes there is not much traffic in the system. Now, if you create a table with 100 RCUs and you see a spike of traffic greater than 100 RCUs, then whatever is above 100 RCUs will get rejected, right? So that's what it means. That's what I mean by non-uniform traffic over time. So essentially what's happening is maybe your traffic is getting distributed across all the partitions, or maybe it's getting to a bunch of partitions, but it is not uniform across time, which means if you have provisioned the table at 100 RCUs, any request that is being sent above the 100 RCU limit, it will all get rejected. Another challenge, what we saw was now customers to solve this problem of seeing that they are getting throttled. To solve this problem of getting throttled, what they did was they started provisioning for the peak. And instead of doing 100 RCUs, they would ask for 500 RCUs, which means that it is able to handle the peak workload that they'll see in the day, but at the same time, for the rest of the day, you are seeing a lot of waste in the system, right? This meant a lot of capacity unused, a lot of capacity wasted, which incurred cost to the customers. And customers asked to us, hey, can you solve this problem? So we said, okay, what if we let the customers burst? So what is the capacity of the bucket? To help accommodate the spike in the consumption, we launched bursting, where we allow customers to carry over their unused throughput in a rolling 5-minute window. It's very similar to how you think about like unused minutes in a cellular plan, right? You're capped, but if you don't use minutes in the last cycle, you can move them to the next one. And that's what we called as the burst bucket. Now, effectively, the increased capacity of the bucket was able to help customers absorb their spikes. So you have 2013, this is 2013 timeframe where when we introduce bursting, unused provision capacity was banked to be used later. And when you exercised those tokens, your tokens will be spent, and finally, that particular problem of non-uniform workload over time, we were able to solve it. Now, we talked about the non-uniform distribution over time. Let's talk about non-uniform distribution over keys. So let's say that you're running a census application for Canada, and the data of the table is partitioned based on zip codes, right? Now you can see in this map, 50% of Canadians live below that line and 50% of Canadians live north of that line. So which means what you'll see is that as the most of your data is essentially going in a bunch of partitions, right? And which means your traffic on those partitions will be higher as compared to your traffic on some partitions. So in this example, we have 250 RCUs going to the green partition, but 10 and 10 RCUs going to orange and pink partition. So your overall, the partitions, they're not seeing uniform traffic. And the takeaway that we had from bursting and non-uniform distribution over space was that we had essentially tightly coupled how much capacity a partition will get to how the physically we are basically landing these partitions. So we had essentially coupled partition level capacity to admission control, and admission control was distributed and performed at a partition level. What that resulted in, just a pictorial picture of that, is you would see all the traffic going to a single partition, and then since there is not enough capacity on that partition, the request will start getting rejected. The key point to note here is that even though a customer table has enough capacity, for example, in this case, 300 RCUs, but that particular partition got only assigned 100 RCUs, so that's why their requests are getting rejected, and customers were like, hey, I have enough capacity on my table, why is my request getting rejected? And this particular thing was called as throughput dilution. And so the next thing we had to do was solve throughput dilution. And to solve throughput dilution, what we did was we launched global admission control. So DynamoDB realized it would be going to be beneficial to remove the admission control from partition level and move it up to the request router layer and let all these partitions burst. Still have a maximum capacity that a single partition can do for workload isolation, but move the token buckets from the partition to a global table level token bucket. So in the new architecture, what happens is we introduced a new service called as GAC, Global Admission Control as a service. It's built on the same idea of token buckets, but the GAC service centrally tracks the total consumption of table capacity, again in terms of tokens. And each request router, it maintains a local token bucket to make sure the admission decisions are made independently and communicate with GAC to replenish the tokens at regular interval. And GAC essentially maintains an ephemeral state computed on the fly from the client requests. So going back to the 300 RCU example, now customers could drive that much traffic to even a single partition because we moved the token bucket from the partition level to a global level, which is a table level bucket. With that, no more throughput dilution. A great win for customers, right? Well, that particular solution was amazing. So we had essentially launched bursting and we did global admission control. And it helped a lot of use cases in DynamoDB. But still, there were cases where a customer would still, due to maybe non-uniform distribution over time or space, would still run into scenarios where traffic to a specific partition is, reaching its maximum. So if a partition can do 3000 RCUs maximum, and customer wants to do more on that partition, request greater than 3000 RCU would get rejected. And we wanted to solve that problem as well. So what we did was, as the traffic increases on the partition, we actually split the partition. Instead of throttling the customer, we started doing automatic splits. And the idea behind automatic splits was that to identify the right midpoint, which will actually help to redistribute the traffic between two new partitions. And if customers send more traffic to one of the partitions, we would again further split that into smaller partitions and route the traffic to the new partitions. So now you have these partitions that are, equally sized, or they're balanced essentially, and you as a developer did not have to do any single thing. So AWS literally is adjusting the service to fit your custom needs on the specific usage pattern that you are generating for the service. And all this magic happens to solve both the problems, even if you have non-uniform traffic over time or non-uniform traffic over space. And this is not something that we got right from day one. As more and more customers built on top of DynamoDB, we analyzed their traffic, understood the problems that they were facing, and solved these problems by introducing bursting, split for consumption, and global admission control as solutions for all these different problems. So going back to the picture, where if the customer is driving 3000 requests per second to the green partition, we would automatically split, identify where exactly is the right place to split that, and split it so that 1500 RCUs, the traffic splits between the two. This was, again, amazing. We essentially did a bunch of heavy lifting on behalf of the customers. One thing we still were hearing from customers that, hey, DynamoDB has figured out a lot of things for us. Now, for us, coming from the world where we are always have been thinking about servers, now you've started asking us to think in terms of read capacity units, write capacity units. Can you further simplify that? So instead of asking customers to specify provisioning at the time of table creation, what we did was we launched on demand, where you don't even have to specify that. All the innovations that we did around bursting, split for consumption, global admission control, all of those enabled us to launch something which is basically on-demand mode on your tables, where you just create a table and start sending requests, and you pay per request for that particular table. So the key lesson here is that designing the system which adapts to the customer traffic pattern is the best experience that you can provide to the customer who are using the database, and DynamoDB strives for that. And we, as I said before, we did not get this right in the first place. We launched with the assumption that traffic will be uniformly distributed, but realized there are actually non-uniform traffic distribution based on time and space. And then analyzing those problems, making educated guesses, we evolved the service and solved all these problems so that customers, all the heavy lifting, all the essential complexity is moved away from the customer into the service, and customers, they just get a magical experience. Now, let's jump into another topic, which is about availability. I said DynamoDB provides high availability. Let's look at how DynamoDB does that. Now, DynamoDB has evolved, and a lot of customers have moved the mission-critical workloads into DynamoDB. And AWS, there are service disruptions that happen. 2015, DynamoDB also had a service disruption. And as I said in the beginning, whenever there is a service disruption that happens, we try to learn from them. And the goal is to make sure that the impact that we saw doesn't repeat. We want to make sure the system weaknesses are actually fixed, and we have a more highly available service. So when this issue happened, one of the learnings that we had from that particular COE was that we identified a weak link in the system. And that link was related to caches. And these caches are essentially the metadata caches that we had in the DynamoDB system. And one thing about caches is that the caches are bimodal. There are essentially two routes that a cache code can take. One is when there is a cache hit, your requests are served from the cache. So in the case of metadata, all the metadata that we request routers wanted, it was being served from the cache. And then you have a cache miss case where all the requests actually go back to the database. And that's what I meant by the bimodal nature of the caches. And bimodality in a distributed system is a volcano waiting to erupt. Why do I say that? So this is the, going back to our put item request. So whenever a customer made a request to DynamoDB to put an item or get an item, the request router is the first service where that request lands. Now, request router has to find out where to route the request. What are the storage nodes for that particular customer table and partition? So it will hit a metadata service. Now, to optimize that, DynamoDB also had a partition map cache in the request routers. The idea is that if a particular, since the partition metadata doesn't change that often, it's a highly cacheable workload. And DynamoDB, we actually had about 99.75% cache hit ratio from these caches which are on the request router. So whenever a request lands on a brand new request router, it has to go and find out the metadata. And instead of just asking the metadata for a specific partition, it would ask the metadata for the full table, assuming that next time customer makes a request for a different partition, it already has that information, right? And maximum 64 MB request you can get. And we don't have just one request router, as I said, we have like multiple request routers. And if a customer creates a table with millions of partitions and starts sending that many requests, they'll probably hit not just one request router, they'll hit multiple request routers. And all those requests then request routers would start asking about the same metadata, which means you have essentially reached a system state where you have a big fleet talking to a small fleet. So the fundamental problem is that whenever either there is nothing in the caches, i.e. the cache hit ratio is 0, you have a big fleet driving so many requests to a small fleet, and a sudden spike in traffic. In steady state, it was 0.25%. If the cache hit ratio becomes 0, caches become ineffective, traffic jumps to 100%, which means 400x increase in traffic. And that would further lead to cascading failures in the system. So the thing that we wanted to solve is remove this weak link from the system so that the system can always operate in a stable manner. So how did we do that? So what we did was two things. One is, as I said previously, in the previous version of DynamoDB, the first version, request router would load whenever it finds out that there is no information about the partition which it wants to talk to. It would load the full partition map for the table. First change we did was, instead of asking for the full partition map, just ask for that particular partition which you are interested in. That was the one change that we did, and it was a simpler change. We were able to do it faster. And then we also secondly built an in-memory distributed data store called memds. And memds, it stores all the metadata in memory. Think of it like an L2 cache. All the data is stored in a highly compressed manner. The memds processes on a node encapsulates essentially a Perkle data structure, and it can answer questions like, hey, for this particular key, which particular partition it lands into, so that memds can respond back to the request router the information, and then request router can route the request to the corresponding storage node. Now, we still do not want to impact performance, right? So we do not want to make a off-box call for every request that customer is making. So we still want to cache results. So we introduced a new cache, which is called the memds cache on these request routers. One thing which is different and critical, the most important thing which we did different here on these caches is that even though there is a cache hit on the memds cache, we would still send all the traffic to the memds system asking for the information, even though we have a cache hit on these memds nodes. What that is doing is essentially the system is generating always constant load to the memds system. So there is not a case where suddenly caches become ineffective, your traffic suddenly rises. It is always acting like the caches are ineffective, right? And that's how essentially we solve the weak link in the system of metadata getting impacted by request being like landing from multiple request routers onto the metadata nodes. So overall, the lesson here is that designing systems for predictability over absolute efficiency improves the stability of the system. Like while system like caches, can improve performance, but do not allow them to hide the work that would be performed in their absence, ensuring that your system is always provisioned to handle the unexpected load that can happen when the caches become ineffective. So with that, conclusions / key takeaways. We talked about the first and second. The first one being adapting to customer traffic patterns, improve their experience, and we looked at it with how different problems we solve by introducing global admission control, bursting, and finally on demand. Second, designing systems for predictability over absolute efficiency, improve system stability. That's the one we just saw with caches. Caches are bimodal. How it's important to make sure that system is doing predictable load and the failure scenarios are tamed by making sure that your system is provisioned for the maximum load that you have to do. Third and fourth, these are two more things that we talk about in much detail in the paper. The third being DynamoDB is a distributed system. We have multiple storage nodes, multiple request routers. Performing continuous verification of data at rest is necessary, and that's the best way we have figured out to ensure we meet high durability goals. Last, maintaining high availability as system evolves. It might mean that you have to touch the most complex part of your system. And in DynamoDB, one of the most complicated, most complex part is the Paxos protocol, the multi-Paxos protocol. And to improve availability, we had to do some changes in that protocol layer. And the reason we were able to do those changes easily was because we had formal proof of these algorithms that are being written there, that were written there right from original days of DynamoDB. And that gave us quite high confidence. Since we had a proof of the working system, we could tweak it and make sure that the new system still ensures correctness, all the invariants are met. With that, thanks a lot for listening, tuning in, and I am happy to take any questions. Either you can ask me questions now, meet me here, or you can tweet you can tweet directly to me at Akshat Vig. With that, thanks a lot, and I'm here to take any questions. Thank you.
Hello. Well, Akshat, this is a wonderful talk. Thank you again for giving this. We have tons of questions lined up, and let's just go through some of the questions that the various folks had. I'll go in the order that I recorded them and the way they were asked. But someone asked, what storage system does metadata storage use? I think you answered this, but you can go into more detail here.
Yeah, so DynamoDB uses DynamoDB for its storage needs. So just think about it, the software that is running on the storage nodes, that's the same software which is running on the metadata nodes as well. And as we have evolved, as I talked about MEMDS being introduced in the later parts of the slide, That's the basically think of it like a cache, an L2 cache on top of the metadata that is being used to serve like partition metadata for all the learnings that we had in scaling bottlenecks with the metadata fleet.
Got it. So, like the metadata nodes, you're saying it's just another Dynamo system, or is it just a storage system? Like, does the metadata service come with its own request router and storage tiers, or is it just, yeah?
No, it's just the storage node software. Request router basically has a client which talks to the storage nodes. It uses the same client to talk to the metadata node, so that whenever the request comes, it's exactly same code that we run for like a production customer who would be accessing DynamoDB.
Excellent. Okay. Since we're on the topic of MMDS, someone asked, is MMDS eventually consistent? How does it change to a cached value addition of a new value of one MDS node get replicated to other nodes?
Yeah,
Essentially,
so
what's the
MemDS,
consistency model?
yeah, MemDS is built using, I would say, think of it like you have an L2 cache, and that cache is updated not a write through cache, but a write around cache. So whenever a write happens on the metadata fleet, which is like very low throughput, partitions they don't change often, right? So what happens is whenever a write happens on the partition um, table in the metadata store, that those writes through streams, they are basically consumed by a central system which sends all the memds nodes to have the updated values, and this whole process happens within like milliseconds again. As the change comes in, it just gets replicated on all the boxes. So the guy which is in the center is responsible for making sure all the memds nodes are getting the latest values until it is acknowledged by all the nodes. That system doesn't move forward. So
Hmm.
that's how the
Do you employ partitioning and I guess master slave sort of models there, or other agreement protocols? Like,
it's
or does
all
every MDS node have all of the data?
memds has all the metadata, so every node has, it's basically vertically scaled. Every node has, because the partition metadata, as I said, is like not that big, it's tiny. The main thing there is the throughput that we have to support. That's what is very very high. That's why we just keep on adding more read replicas there. And yeah, so it's not the leader follower configuration. It's like
Hmm.
every node is eventually consistent, it's a
Hmm.
cache, and they are scaled for specifically the reads that metadata request have to be served for whenever customers are sending request, or any other system which wants to access the partition metadata.
So if I understand, so there's some coordinator that's in the MemDS system. A request is sent with a new write request. That coordinator is responsible for ensuring that all of the entire fleet gets that data.
Yes,
It's
exactly.
coordinator's job. It's not each peer-to-peer kind
Yeah,
of gossip type protocol to link.
yeah,
So that coordinator is kind of responsible for durable state and consistent state.
yep,
Well, I guess
yeah.
each node, once they get it, they're durable, but that's just for consistent state transfers.
Yeah, and durable in the sense it's a cache. So when it crashes, it'll just ask from the other node in the system to get up to speed and then start serving requests.
Okay. And oh, that makes sense. And that coordinator, how do you make, everyone always asks in distributed systems, how do you make that reliable?
So all these writes are idempotent. Again, so you could have like any number of these guys running in the system at any time and writing to the destination. Since the writes are idempotent, they always monotonically increase, so never goes back. So if a partition has changed from P1 to P2, if you write again, it will say, hey, I have the latest information, I don't need this anymore. So we don't need a coordinator, we try to avoid that.
Oh, so you don't have a coordinator service that's writing to these nodes.
Like we don't have the leader configuration there, leader and follower configuration there.
You don't have that, right?
Coordinator, yeah, yeah,
But you do have a coordinator that all
yes,
requests go to, and
yeah,
that keeps track of the monoticity of the writes, like a write-ahead log. So it's got some sort of distributed, reliable write-ahead log,
yep.
and it's just somehow sending it. Would that be a topic of another talk that you may give? I mean, that
I think
itself is
global tables is what I hear a lot. We did transactions, yeah. So I think we should probably figure out another talk as a follow up at another QCon. I'd be happy to come.
okay. Cool. So that was sort of the MemDS stuff. Were there any other items, or I'm curious if there are any other questions people have about MemDS while we're on the topic? I don't see. Oh, someone did ask this question. So when the partition grows and splits, how do you ensure the metadata, MemDS cache layers get updated consistently?
Yeah, as I said, it's eventually consistent, and the workflows that are actually doing like partition splits and all these things, they wait until MemDS is updated before flipping the information there. So
Okay.
other thing is, even if the data is not there in MemDS, storage nodes also have the protocol to respond back to the request router saying that, hey, by the way, I am updated. I don't host this partition anymore, but this is the hint that I have, so maybe you can go talk to that guy. So even if for like the edge cases where this information might get delayed, we still have mechanisms built in the protocol
to update the coordinator. So each partition also has some information of who else has this data.
Yes, just about
partition, but each MemDS node.
MemDS node. Yes. Yeah.
And also, I guess it's a little easier because this, unlike DynamoDB, this can be eventually consistent. DynamoDB has, people care about consistency over, I guess, availability and other things. Okay, so essentially we're saying that so when you split, it doesn't have to be replicated everywhere immediately. It's done as time. So actually, I had a question about that. When you do a split, are you rebalancing?
Sorry to interrupt. We've run out of time on this session, I'm afraid, Sid. So we can continue the conversation in Slack. It's just people will be coming in for the next. We'll be leaving for the next session.
Okay. Akshat, you have all of these questions. You can. You want to go into the channel? And you can answer there. People can join the. What is it called? Track architecture you've always wondered about. People can ask questions here. I can post this sort of question list I have. If you want one consolidated place to see it. But yeah, let's do that. Well, Akshat, thank you so much for your answers. I have so many more questions, but I think we'll take it to Slack for the rest.
Sounds good.
Thank you very much.
Thanks.